Welcome everybody. Welcome again to the course of Extractive Metallurgy. Welcome again to our course. We are going to continue with the classes. For today, we are going to talk about the hydrometallurgy. Hydrometallurgy as very important point in the Extractive Metallurgy course. Okay. It's important to define that hydrometallurgy is a very important branch in the Extractive Metallurgy because it's all related about how the solids could be solved in the liquids, mainly water. The idea is to how to use water or water solutions in order to obtain minerals from the solids. The hydrometallurgy is a very important method to obtain metals, but it's not very old. It's of course, hydrometallurgy is older than the hydrometallurgy because hydrometallurgy is recent. And the processing from in a scientific way is a technique that is relatively young. Could be we could find some application of hydrometallurgy from the oldest civilizations. For instance, in China's in Han Dynasty, we have some indices, some ideas, or some knowledge about how to use water in order to obtain metals. But it's not easy to have a very repeated way or a very usual method to obtain metals. Really, we could obtain or have knowledge about hydrometallurgy to obtain salts or to obtain some metals, but it was occasionally used, not in a permanent way. Okay, and it was easy to obtain or to have some indices during the Middle Age, of course, and in the Middle Age was very important the use of aqua regia. Aqua regia is a combination of chloric acid and nitric acid. We are going to show you in a little more about that. But it's a relation 3-to-1, chloric acid versus nitric acid. And it was very useful or very common to dissolve gold during the Middle Age. Nowadays, it's used in order to obtain gold, or better to define the quantity of gold that you can have in a special sample. But really, the obtention of gold, the obtention of silver with metallurgy, with hydrometallurgy was later in the 19th century. Also, in the past, was used the water in order to evaporate water in order to obtain some kind of salts like potassium or something like that. Okay, but really the goal of hydrometallurgy could be established at the end of the 19th century. At the end of the 19th century, 1987 and 1887, it was established the principles of cyanidation. The principles of cyanidation could be defined as the beginning of the modern hydrometallurgy because it was developed by John Stewart MacArthur and some the brothers Robert and William Forrest. They established the methodology to dissolve gold in cyanide, and that was the most important issue to start to define that hydrometallurgy was a special science, and it's very important that part. And the other is use zinc in order to precipitate or cement the solution in order to obtain it. Okay. Of course, or in the second part of the 19th century, also was established the methodology to obtain alumina from bauxite. The methodology to obtain alumina from bauxite is the Bayer process, and it was established defined at the end of the 19th century. Was important. Okay, which are the theoretical foundations about the hydrometallurgy process? The most important is to define which are the most important activities in order to obtain metals, in order to obtain minerals, making solutions for solids. Okay, the most important is to define that this process is establishes in low temperature. Okay, you don't need to elevate the temperature. The temperature is until 200 degrees centigrades Celsius, 250 Celsius. No, but and the other is atmospheric pressure. Atmospheric pressure in order to define the characteristics of that kind of process. Okay, this is the most important. If we are going to make a hydrometallurgical processing, the most important is you are going to react a solid with a liquid. It's a non-heterogeneous, it's a heterogeneous reaction because you have solid and liquids. And could be possible if you are going to make some solvent extraction, you could have liquid and liquid reactions. Okay? In some cases, could be possible to have gases, but it's not common. The common is solid and liquid. This is the most common process in hydrometallurgy. And sometimes liquid and liquid, but always liquid is present. Okay, this is the most common. Which are the elements to define the chemistry of solutions that could be applicable to the hydrometallurgical process? Okay, in hydrometallurgical processes, the most important thing is that this is an heterogeneous reaction. This is the most important thing. Okay, and in order to define, to study the phenomena, you have to study the solid and you have to study the liquid. The liquid is the water. Is the most important thing. The liquid is the water. And the idea is to study the characteristics of the solids and study the characteristics of the liquids. And that is the thing we are going to present now. Okay, first of all, we are going to study the solid. When you study the solid, when you define the solid, you need to know a little more about the bonds, the structure of the solid. Which are the bonds that make the equilibrium in the solid? In the different minerals, we could classify the minerals in base of the characteristics of the bond. Which are the bonds that you have in the solid, in the mineral that you are going to make the treatment. And the bonds could be metallic bonds, ionic bonds, and covalent bonds. This is the typical kind of bonds we have. And it's important to say that not always is possible to have pure metallic bonds, or pure ionic bonds, or pure covalent bonds. No, maybe it could be possible to have mixtures, to have the bonds mixed, and it's important to have. It's common to have that kind of situation, and it's important to define which are the predominant bonds in the structure. If we are going to study metals, of course, the kind of bond we have in metals is the metallic bond. The metallic bond, when you are present the bond, when you are studying the bond, we have some characteristics of the bond. Okay, first of all, the electrons are in movement. The electrons are moving every moment, and there are no directions clear between the bonds, between the how the electrons are bonds. They are moving, and it's important to present that characteristics. In the metallic bond, the electrons are not localized. They are really delocalized. uh, they don't have a special position. They have different kind of position because of exists a high electronic conductivity of the crystals, and it's important to define that. Okay. The other is the atoms with that are linked, that are bonded with a metallic bond. They have usually low electronegativity. Remember, the concept of the electronegativity is very important to define because and it's usual that the metals have different electron balance. That is important to define the characteristics of the electrons. Okay, important to say. And the other characteristics of the minerals that have metallic bond is the usually minerals are the minerals are solid state. At room temperature is the general case. Some cases there are some metals like mercury are liquid, but it's not common. The common is metals are liquid. This is most important. The metals have high electric conductivity, and thermal conductivity, and that is consequence of the mobility of the electrons, and it's important. And another characteristic of the metals is the metals present some metallic shine in order to because they reflect very well the light. It's important. Okay. Another characteristics of the metals or the metal or the metallic bond is they are the mechanical answer or the mechanical when you push mechanically they are ductile. They have a ductile behavior. They are malleable because they change the position. They move the electrons and could be possible to have an elastoplastic behavior. And because it's easy, they change the condition of the position of the electrons, and that's important in that kind of planes. The other kind of metal, the other kind of bond, sorry, is the ionic bond. The ionic bond is very important in metals because this kind of bond is possible when the elements that are linked by this kind of bond, they have a high difference of electronegativity. This is very important because the idea is one of the elements lose the electron and the other element wins them. And that's the position. This is the case of the sodium chloride. When you have sodium chloride, sodium is in the group number 1 of the periodic table, and chloride is in the group 7. What it means? Sodium has 1 electron in the so superficial level of energy, the last level of energy, they have only 1 electron, and chloride has 7 electrons in the last level of energy. What it means? They have the possibility to sodium lose the electron and chloride wins the electron, and they are in a position that they are in equilibrium. Okay, that's important to define the stability of this kind of bond, the ionic bond. These crystals, this metal, these elements that are linked and bonded by ionic bond, the crystals are relatively hard. They are really hard. They melt is not easy to melt. They have temperature, high temperature in order to be melt, and it's difficult. They are not good, very good conductor. They don't conduce temperature or heat. This is the characteristics of this kind of elements that are linked by ionic bond. And what it means, they are very easy to solve in water because water is a polar solvent. When the elements or when the rocks or minerals are linked by ionic bond, they are easy to be solved because they are linked by electrostatic forces. When you put in a solvent, a polar solvent, immediately they are they form immediately a material that can ionize, and it's important to define that because they move easily, the electrons move easily. And the ionic bond, as we can see in the figure, it's important that the element stay in a equilibrium position by convenience. The sodium in this case that has only one electron in the last level of energy easily lost this electron. And in the other case, in the fluoride easily gain or win the electron. It's important to define. This is very common in the salts, and immediately the element that are linked to the compound that is usually bonded by this kind of electronic this kind of ionic bond is possible to define this kind of characteristic. Okay. This is a good example how the elements could be linked by ionic bond. The elements that are linked in this way have very high difference in electronegativity. Elements in the group number 7 in the periodic table have very high electronegativity values, and elements in group number 1 and number 2, the electronegativity is relatively low. Okay, and the other kind of bond is the covalent bond. Since the point of view of the hydrometallurgy, this is the less attractive kind of bond because covalent bond are the covalent bond is the characteristic of this kind of bond is the electrons are sharing. The electrons are they are sharing the electrons, and the equilibrium is carrying in a very stable way. When you have a covalent bond, you have a very stable material, and they have a very high temperature. When you have this kind of bond, the electronegativity or the elements that are linked in this kind of bond are very similar. The electronegativity is very similar. What is that? That they are very stable, and it's very difficult to melt by increasing the temperature because they are very stable. They are very stable. They are solids at room temperature, and another characteristic is the low mobility of the electrons. The electrons don't move, and if the electrons don't move, they don't have the possibility of being good. They don't have very conductivity. The conductivity is very low. Thermal conductivity and electrical conductivity. This is the one characteristic. Another characteristic is that these kind of solids are opaque and they are not transparent. And since the point of view of mechanical behavior, they are rigid materials. They are not like metals. Metals are, they have a elastoplastic behavior, but the minerals are linked by a covalent bond. The behavior is very elastic, not plastic, because the deformation is very it depends only the stress and the elasticity modulus is very high. Okay, it's one characteristic. From the point of view of hydrometallurgy, as I told you, it's very difficult to use this kind of minerals in this technique, this processing. We don't like covalent bonds in order to obtain or to work with hydrometallurgical processing. This is the characteristic of in this periodic table. We can see the characteristics of this. Okay? But as I told you at the beginning of this conference, pure bonds are not common. The most common situation is you have a mixture of different kind of bonds. Maybe we can possibility of have metallic and ionic bonds, as for instance in some kind of sulfurs, lead sulfurs as galena, sphalerite, chalcopyrite. They are very good examples how to work mixed bonds. It's important. And the other is the covalent and ionic bonds, submission of that, like as in carbonates. When you have calcium carbonates, or limestone for instance, when you have calcium carbonates, you have a mixture of covalent and ionic bonds. It's a mixed bonds, and sometimes it's not easy to work. In that kind of thing, it's not easy to use hydrometallurgical process. And the other is metallic covalent bonds, as pyrite. Pyrite is some kind of sulfurs, have this kind of characteristics that is not common, but also it's difficult to use hydrometallurgical processing in order to obtain this kind of materials. Okay, this is important to define. We have to define the percentage of the different bonds. What percentage of ionic, of which percentage of covalent, of which percentage of metallic bond. For hydrometallurgy, we prefer ionic bonds and metallic bonds, and the mixture, metallic and ionic bonds. But when we have covalent, it's difficult. We have covalent metallic, is difficult, or covalent ionic is difficult. Okay, this is one of the characteristics. Okay, this is the point of view of the solid. Now we have to define or look for the characteristics of the water or the solution. We have to study both solid and solution and water. Okay, water is the most important solution in a hydrometallurgical process, and water is the reactive most important, is the solvent of the reaction. And it's important to define how the water works. Water is a very common substance, but it's a very important liquid for life, for every day, for daily life. And it's a combination of hydrogen and oxygen. It's important to define that. And we could say that is the most abundant component in the structure of the surface, the crust, because we have a lot of water. We have different quantities of water in different conditions, but it's the most important substance we have in the air. And we have to know a little more, and we have to define the characteristics of the water in order to obtain or to how to obtain different conditions. We have water in different states. We have in different phases. We have solid in the air, in pools, in glaciers. We have water in liquid phase. It's very common in rivers, in the sea, in lakes, and we have a lot of water also in gas, phase, and in gas, in clouds, some kind of fogs, and we could use the different phases of the water in order to work. This is a phase diagram of the water, and here we can see the conditions in pressure and temperature in order to define the phases, the stability of the phases of the water. Solid phase, liquid phase, and gas phases. And we have to define the critical points or the equilibrium lines, the equilibrium points, the equilibrium lines, in order to define how it's possible to move from solid to liquid, or liquid to gas, or maybe also to solid to gas. This is the water has some different properties, physical properties and chemical properties. Since the point of view of physical properties, water is odorless, it's an odorless liquid. In tasteless, they don't have color. In normal condition, atmospheric pressure, it's possible to pass from solid to liquid at 0 Celsius to 273 Kelvin, and pass from liquid to gas. The boiling point is 106 Celsius, 373 Kelvin. And the density of the water is 1 gram for cubic centimeter. And is the maximum value is of 4 Celsius. Okay. The water has another important properties like caloric capacity is very important. More than a lot of liquids, and this is one of the most important properties that we have. The latent heat of evaporation is high relative and relatively with other liquids, and it's important in order to work with the hydrometallurgical process, because we have the possibility to maintain the liquid state in increasing the temperature. The water continue liquid. This is the some of the physical properties. And another important thing is about chemical properties. From the chemical point of view, water is important because they have a very high capacity of dissolution. And this is the key in the hydrometallurgical process. Water is used to dissolve a lot of different elements, because the universal solvent, okay? Because a lot of substances are soluble in the water, okay? And it's important to say that since the chemical point of view, water is possible to combine with salts, salts, hydrates, reactions with some metals, react with acids, and maintain or create special kind of reactions. It's important to say. Since the point of view of the structure, the water is not a symmetric molecule. It's the molecule is a special position because it's conformed by hydrogen and oxygen, and the oxygen, the two atoms of oxygen are located in the same side, and that the atoms of oxide have a negative charge, and the hydrogen has a positive charge. And it's important to say that means that the water is a polar solvent, and it's important to define that because it's possible. This is one of the keys that permits for us to work in hydrometallurgy, because water is a polar solvent, and it's important. Okay, exists. The water has different conditions of pH scale, water ionization. Really, the water has different characteristics of the solvent. The pH is important because water has certain pH. Less is neutral. The pH in the water is neutral. We have possibility to have water solution with a very low pH in order to increase the acidity if the pH is low, and if the pH is high, it will increase the alkalinity, and it could be possible to have water solutions. Okay, another topic is that could be important to define some characteristics of the water in order to work in hydrometallurgy are the electric constants. I'm going to present the ideas and present the concepts, but I'm not going to develop it, or I invite you to study. The other is the solubility of the different elements in water. We have to study this. Yeah? And this is important to define in hydrometallurgy, study the general rules of solubility in order to define how gases, liquids, or maybe solids could be has solubility in the water. Maybe how the polar molecules work, the no-polar molecules work, and some ionic crystals. Ionic crystals are very important for us in hydrometallurgical process. The other is non-ionic crystals, how it works, it's important to define that. And what happens when we have organic solvents. Okay. And the ionic force to define that. Okay, this is the topics we have to explain and to know about water, the product solubility, and of course the effect of sharing ions in the formation of some complex. When you are working with solubility, when you are working in hydrometallurgy, you have to define this kind of thing. Okay, this is the most important concept that we are going to consider here in order to study hydrometallurgy. We work with the solid and we work with the liquid, in this case the water. In the solid, remember, we talk about the bonds, what kind of bonds. The most important are for in hydrometallurgy process are the ionic bonds, and the water, the liquid, the solvent, is water and his physical and chemical properties to work with hydrometallurgy. Okay, this is the most important thing to define. And with this concept, we are going to finish the characteristics or the general concepts in hydrometallurgy in order to present the most important processes in this kind of process in electrical metallurgy. Okay, thank you very much. I invite you to continue working with us in this course of Extractive Metallurgy. Thank you very much. Have a good day, and I wait for you in the next episode. Thank you. Bye.